Hey, my name is Rishi Patel, and this is my video lab report for Lab 4, Circuits and Capacitor. The purpose of this lab is to use principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel. The segments for this PowerPoint contain the introduction, fundamental concepts and principles, the experiment part 1 and part 2, and of course the discussion. For the overall results, I found that energy is conserved. Fundamental concepts and principles include the node rule, which means that the current in is equal to the current out, the loop rule, which is the summation of all the voltages is equal to zero, Ohm's law, the potential difference for capacitors, and also a specific formula used for linearization, also finding the value of RC. For the first part of the experiment, I designed a circuit that contained two 1.5 voltage batteries, two ammeters, and also two resistors. The first resistor had a resistance of 47 ohms, while the second one had a resistance of 100 ohms. I predicted that the amps for I1 and I2 would be equal to 0.02 amps, and this was proven from the simulation to the right. Also, reversing the ammeters still resulted in a current of 0.02. Next, I replaced one of the ammeters with a voltmeter. The voltmeter read 3 volts while the ammeter read 0. This is because the circuit is not fully connected and the current stops flowing to the ammeter. Next, I found the potential difference around the circuit at given intervals. From B to C, it is 0 volts. From C to D, the voltage is 0.96. From D to E, it is also 0, and from E to F, it's 2.04 volts. From F to A, it is also 0 volts. The resistors give us a difference in voltages, but the idea is that they should add to 3 volts, which is the total amount of voltage in the circuit. This is because of the loop rule. The voltage given from the batteries should equal to the voltages given from the resistors. Here's a graph that compares the volt at a given position in the circuit. As you can see, the voltage only drops at the location of the resistors, which should make sense. This graph also shows that the voltage is conserved. Why doesn't the ammeter reading change when you attach the voltmeter? Because voltmeters have a very high resistance, a small number of current passes through it, which does not affect the readings of the ammeter. When I connected the voltmeter across a 100 ohm resistor, the ammeter read 0.02 amps. What happens to the current through the other ammeter when in parallel with the 100 ohm resistor, and why? Well, the ammeter read 0.06 amps. This occurs because ammeters have zero resistance, so the current does not travel through the second resistor. Instead, it travels through the path of least resistance, which is the path of the ammeter. The resistance for the first resistor comes out to be 48 ohms, while the resistance for the second resistor comes out to be 102 ohms. The resistance for the wire and ammeter is calculated to be 0 ohms. For the second part of the experiment, I am dealing with an RC circuit. For this circuit, I am using a 9-volt battery, a 10 ohm bulb, a 20 ohm bulb, and a 200 millifarad capacitor. When I first connected the battery, the light bulb began to glow bright and soon began to dim until it was fully off. When I disconnected the battery and connected the capacitor directly to the 10 ohm bulb, the light began to glow bright once again, but soon began to dim until it was fully off. When I first connected the battery, the capacitor was charging. The current began to decrease until it became 0. When I removed the battery from the circuit, the capacitor began to discharge. Now the current began to increase as it was leaving the capacitor. For the 10 ohm bulb, it took 11.952 seconds to charge and 11.03 seconds to discharge. For the 20 ohm bulb, it took 16.12 seconds to charge and 18.21 seconds to discharge. For this part of the experiment, I used a 30 ohm bulb and measured the voltage across an interval of 20 seconds. When plotting the data, I used the formula from earlier in order to get a linear graph. The data from the graph gives us an equation of negative 0.1667x plus 0.1584. The slope from this equation is negative 0.16667. To find the value of RC from our data, I did 1 divided by the negative of the slope, and this turned out to be 5.999, which is approximately equal to 6. The actual value of RC is found by multiplying 30 ohms times 0.2 farad, and that value turned out to be 6. The actual value of RC and the RC value from the data is fairly accurate with a low error. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits if you hooked it up?
An ideal ammeter has zero resistance, which is shown in the virtual lab. A real ammeter, however, has some resistance, or our values for current would have been slightly lower because an increase in resistance decreases the current. What if you were doing this lab in real life and use an actual battery instead of in a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Our ideal model would have predicted the capacitor charges instantly. However, in real life, this would not have been the case. The prediction would not have been instant because even batteries have a slight resistance in them. The capacitor would still charge quickly, but not instantly.